Across the disk of the Milky Way, a structure spanning approximately 100,000 light-years from edge to edge and containing between 200 and 400 billion individual stellar systems, there exists a fundamental question that bridges observational astronomy, planetary science, biochemistry, and the deeper philosophical territories of what constitutes habitability itself. Within this vast galactic architecture, rotating once every 225 million years around a supermassive black hole at its center, current evidence suggests the presence of more planets than stars, a population estimate that places the total planetary census somewhere between 800 billion and perhaps 2 trillion individual worlds, each following its own elliptical path through space, each subjected to the particular characteristics of stellar radiation, gravitational influences, and chemical compositions that emerged from the specific conditions of its formation. The question of how many among this staggering multitude might harbour the conditions necessary for life, whether microbial or complex, whether presently active or preserved only in fossil record, whether based on familiar carbon-water chemistry or operating through mechanisms yet unimagined, represents one of the most profound inquiries facing contemporary science, demanding not merely the cataloguing of planets, but the construction of comprehensive frameworks for understanding what life requires, how commonly those requirements appear, and what observational signatures might reveal biological activity across interstellar distances measured in parsecs and light-years. The search begins with parameters that can be measured and modelled, with observable characteristics that instruments both terrestrial and orbital can detect and quantify, characteristics that provide the initial filtering mechanisms for identifying which among the galaxy's planetary population warrant deeper investigation. The habitable zone, that orbital region around a star where liquid water can persist on a planetary surface, serves as the primary selection criterion, though this zone's boundaries shift dramatically depending on stellar type, stellar age, planetary atmospheric composition, planetary mass, and the presence or absence of greenhouse mechanisms that can trap thermal radiation. For stars like the Sun, classified as G-type main-sequence stars with surface temperatures near 5,700 degrees Kelvin and lifespans measured in billions of years, the habitable zone extends from approximately 0.9 to 1.5 astronomical units, a range that encompasses Earth's orbit comfortably while excluding both Venus, where a runaway greenhouse effect has pushed surface temperatures above 700 degrees Kelvin, and Mars, where atmospheric loss has left surface pressures too low to maintain stable liquid water despite temperatures occasionally exceeding the freezing point. For cooler M-type red dwarf stars, which comprise approximately 75% of the galaxy's stellar population and possess surface temperatures between 2,500 and 3,800 degrees Kelvin, the habitable zone contracts inward, sometimes to within 0.1 astronomical units of the stellar surface, bringing planets into regions where tidal forces can lock rotations into synchronous states and where stellar flare activity can strip atmospheres over geological timescales. For hotter, more massive stars of spectral types F, A, or B, the habitable zone extends outward, but these stars burn through their nuclear fuel so rapidly, often in mere hundreds of millions of years rather than billions, that the question arises whether evolutionary timescales can produce complex life before the star exhausts its hydrogen core and begins its departure from stable main sequence behavior. Within these habitable zones, distributed across the galaxy's spiral arms, its central bulge, and the scattered population of the stellar halo, observations conducted through transit photometry missions like Kepler and TESS, through radial velocity measurements detecting the gravitational tug of planets on their parent stars, through direct imaging campaigns resolving planetary light from stellar glare, and through micro-lensing surveys that catch the momentary magnification effects when planets pass before background stars, have revealed a planetary population characterized by extraordinary diversity in size, composition, orbital configuration, and system architecture. Rocky planets, those with solid surfaces and compositions dominated by silicates and metals rather than hydrogen and helium, appear to form commonly throughout the galaxy, wherever protoplanetary disks contain sufficient quantities of heavier elements, those elements beyond hydrogen and helium that astronomers call metals, regardless of their actual chemical nature, elements produced through stellar nuclear synthesis and distributed through space by supernovae and stellar winds. Current surveys suggest that approximately 20 to 30% of Sun-like stars host rocky planets within or near their habitable zones, while red dwarf stars, despite their smaller habitable zones and more challenging stellar environments, appear to host rocky planets at similar or possibly higher rates, with some estimates suggesting that nearly every red dwarf may have at least one rocky planet within the region, where surface temperatures permit liquid water under appropriate atmospheric conditions. Scaling these percentages across the galaxy's stellar population, accounting for observational biases that make smaller, more distant planets harder to detect, and incorporating the reality that many stars exist in binary or multiple star systems, where planetary orbits may be disrupted or rendered unstable, yields estimates suggesting the Milky Way contains between 40 and 80 billion rocky planets, orbiting within their stars' habitable zones, a number that staggers comprehension while simultaneously representing only a small fraction of the galaxy's total planetary population. The presence of a planet within the habitable zone, while necessary under conventional definitions of habitability, proves far from sufficient for ensuring conditions where life might emerge or persist. For the habitability of a world depends on an interlocking system of factors that includes atmospheric retention, magnetic field generation, plate tectonics, volatile delivery, impact history, stellar stability, and the particular chemical inventory available during planetary formation and subsequent geological evolution. Atmospheric retention, the capacity of a planet to hold gases against the combined threats of thermal escape, where high-altitude molecules achieve velocities exceeding escape velocity, and non-thermal escape, where stellar wind particles and radiation strip atmospheric components directly into space, depends critically on planetary mass and composition, with more massive planets exerting stronger gravitational pull that prevents atmospheric loss, while planets lacking protective magnetic fields suffer enhanced stripping when stellar wind particles interact directly with atmospheric molecules rather than being deflected around the planet by magnetic field lines. Mars provides the cautionary example here, a planet that possessed a thicker atmosphere early in solar system history, an atmosphere that supported liquid water flowing across its surface and pooling in lakes and possibly oceans, but that lost most of its atmospheric inventory over billions of years after its internal dynamo. The churning motion of liquid metal in its core that generates magnetic fields ceased operation, leaving the planet exposed to solar wind stripping that gradually removed most of its air and reduced surface pressure to levels where liquid water cannot exist in stable form. Magnetic field generation appears to correlate with planetary size, with internal heat, and with the presence of liquid metallic cores undergoing convective motion, factors that depend on initial planetary composition, on the abundance of radioactive elements providing long-term internal heating, and on the thermal evolution that determines how quickly planets cool and solidify through time, raising the question of what fraction of habitable zone rocky planets retain active magnetic dynamos over timescales measured in billions of years. Plate tectonics, the system of moving crustal segments that recycle surface material into planetary interiors and bring fresh material to the surface, appears to play crucial roles in maintaining long-term habitability through its regulation of atmospheric carbon dioxide concentrations via the carbonate-silicate cycle, through its role in generating diverse geological environments that might facilitate the chemical complexity required for life's emergence, and through its capacity to maintain internal heat flow that powers magnetic field generation and volcanic outgassing. Earth's plate tectonic system operates through a complex interaction between mantle convection, crustal density variations, water content that weakens rocks and facilitates subduction, and the particular thermal and compositional structure that Earth's size and composition permit, a system that has operated for at least 3 billion years and perhaps longer, cycling carbon between atmosphere, ocean and interior, creating continents and ocean basins, and maintaining chemical disequilibrium that may be essential for supporting complex ecological systems. Whether plate tectonics represents a common feature of Earth-sized rocky planets, or a relatively rare configuration dependent on factors like water content, planetary mass, internal heat production, and the timing of core formation remains uncertain, with Venus providing an alternative model where a stagnant lid regime, with no plate motion and only occasional catastrophic resurfacing events, has persisted throughout the planet's history, despite Venus possessing similar size and bulk composition to Earth. If plate tectonics proves common among habitable zone rocky planets, the number capable of maintaining long-term habitable conditions rises accordingly. But if Earth's tectonic system represents an unusual outcome requiring specific combinations of mass, composition, and initial conditions, then the fraction of habitable zone planets that remain habitable over billions of years may be substantially smaller than raw orbital statistics suggest. The delivery of volatile compounds, those substances like water, carbon dioxide, nitrogen, and organic molecules that form the basis for known biochemistry, depends on processes operating during planetary formation and early evolution. Processes that include the incorporation of icy material from outer regions of protoplanetary disks during planetary accretion, the bombardment of inner planets by asteroids and comets that carry water ice and carbon compounds from colder regions, and the outgassing of volatile materials trapped in planetary interiors during the heat and melting of early planetary history. Earth's water, comprising approximately 0.02% of the planet's total mass but essential for all known life, appears to have arrived through some combination of these mechanisms, with isotopic signatures suggesting contributions from both asteroidal material formed in the inner solar system and cometary material originating beyond the snowline, where water ice could condense directly from the protoplanetary disk's gas phase. The amount of water a planet receives depends on the particular architecture of its planetary system, on the timing of giant planet migration events that can scatter smaller bodies inward or outward, on the inventory of water, rich material in the protoplanetary disk at the planet's formation location, and on the retention of water against early atmospheric loss during the period when young stars emit intense radiation and powerful stellar winds. Too little water produces a desiccated world where biological processes cannot operate, where chemical weathering proceeds slowly, and where the temperature regulation provided by water vapor, greenhouse effects, and by water's high heat capacity cannot moderate climate extremes, while too much water may produce worlds entirely covered by deep oceans, lacking the continental land masses where diverse chemical environments and nutrient cycling might support complex ecosystems. The optimal water content, if such an optimum exists, remains unknown, but observations of planetary masses and radii suggesting the existence of water worlds with deep, hydrogen-rich atmospheres overlying liquid water layers hundreds or thousands of kilometers deep, worlds unlike anything in our solar system, raise questions about whether life could emerge or thrive in such environments lacking the rock-water interfaces and the chemical gradients that characterize Earth's diverse habitats. The role of stellar characteristics in determining habitability extends beyond the simple definition of habitable zone boundaries to encompass questions of stellar stability, stellar lifetime, stellar metallicity affecting planetary compositions, and the particular spectrum of radiation that stars emit and that planets receive. Red dwarf stars, those M-type main-sequence stars with masses between approximately 0.08 and 0.5 solar masses, present a complex habitability case study combining favourable factors like extraordinary longevity, with lifespans extending into trillions of years, providing vast temporal opportunities for life to emerge and evolve, and their overwhelming numerical dominance comprising 3/4 of all stellar population, with challenging factors including their tendency toward powerful flare events that can deliver intense bursts of ultraviolet and X-ray radiation capable of damaging biological molecules and stripping planetary atmospheres. Their emission spectra weighted toward red and infrared wavelengths that may affect photosynthetic efficiency if life on these worlds employs light harvesting strategies, and their habitable zones positioned so close to the stellar surface that tidal forces likely lock planetary rotations synchronously, producing worlds with permanent day and night hemispheres that experience extreme temperature gradients, unless atmospheric heat transport can redistribute thermal energy effectively. Recent observations of planets orbiting red dwarfs, including the TRAPPIST-1 system, with its 7 roughly Earth-sized planets, 3 of which orbit within the habitable zone, and Proxima Centauri b, orbiting the nearest star to our Sun, have revealed that such planets exist commonly, and that some may retain atmospheres despite their challenging stellar environments. But whether these atmospheres permit liquid water on planetary surfaces, whether they can withstand repeated stellar flare bombardment over billions of years, and whether life could adapt to the particular conditions these worlds present remains observationally unverified and theoretically uncertain. If red dwarf planets can support life, the number of potentially habitable worlds in the galaxy increases dramatically given the numerical dominance of these cool stars. But if stellar activity and tidal locking render these worlds inhospitable, despite lying within nominal habitable zones, then the galactic habitable planet count must be revised substantially downward. Beyond the physical and chemical parameters that define habitability in operational terms, there lies the deeper question of what life requires fundamentally, whether the carbon-water biochemistry familiar from Earth represents the only viable framework for organizing matter into self-replicating, evolving systems, or whether alternative biochemistries operating in different solvents, utilizing different chemical backbones, and functioning under different temperature and pressure regimes might generate living systems that current habitability criteria would exclude. Carbon's capacity to form stable bonds with itself and with numerous other elements, creating the complex molecular architectures that underpin proteins, nucleic acids, lipids, and carbohydrates, combined with water's properties as a solvent capable of dissolving diverse substances, while maintaining liquid state across the temperature range, where chemical reaction rates permit biological processes, has led to the focus on carbon-water life in habitability assessments, a focus reinforced by the absence of any confirmed examples of alternative biochemistry despite centuries of chemical exploration. However, theoretical investigations have examined the potential for life based on silicon rather than carbon, operating in liquid methane or ethane rather than water at cryogenic temperatures like those on Saturn's moon Titan, or life using ammonia or hydrogen sulfide as solvents under different temperature regimes, or life incorporating exotic chemistries at high temperatures and pressures in subsurface environments, raising the possibility that habitable zone definitions based solely on liquid water may exclude vast numbers of worlds where non-water-based life could exist. The discovery of life, even microbial life, operating under principles different from Earth's biochemistry, would revolutionize habitability assessment and potentially expand the count of life-bearing worlds by orders of magnitude. But absent such discoveries, habitability calculations must proceed from the single example available, accepting that this approach may be either conservative, missing many habitable worlds, or potentially overly optimistic, assuming that Earth's particular combination of characteristics appears commonly enough to generate life frequently. The temporal dimension of habitability introduces additional complexity to planetary census efforts. For a world that satisfies habitability criteria at one point in its history may lose habitability as its star evolves, as its atmosphere changes through biological or geological processes, as its orbital configuration shifts through gravitational interactions, or as catastrophic events reset surface conditions, while worlds currently inhospitable may have hosted life in the past or may become habitable in the future as stellar or planetary conditions change. Mars again provides the local example, a planet whose surface features including valley networks, channel systems, crater lakes, and possible ancient ocean shorelines indicate the past presence of liquid water, a planet whose ancient atmosphere was likely thicker and warmer than today's tenuous carbon dioxide remnant, a planet whose first billion years might have offered habitable conditions comparable to early Earth, yet whose present surface proves hostile to life as known, requiring any surviving organisms to retreat into subsurface refugia if they exist at all. Venus presents the opposite trajectory in some climate models, beginning its history as a potentially habitable world with surface liquid water before a runaway greenhouse effect, possibly triggered by volcanic outgassing exceeding the planet's capacity to sequester carbon dioxide in carbonate rocks, or by gradual increases in solar luminosity as the sun aged and brightened, transformed the planet into the inferno observed today, with surface temperatures sufficient to melt lead and atmospheric pressure nearly 100 times Earth's. The temporal evolution of habitability means that a census of currently habitable worlds may undercount the total number that have hosted life at some point in galactic history, while simultaneously complicating the question of whether observers asking these questions will overlap temporally with habitable conditions on other worlds, whether civilizations capable of interstellar communication arise frequently enough and persist long enough that multiple such civilizations exist simultaneously within communication range, or whether the vast temporal scale of galactic history ensures that most life-bearing epochs remain isolated from others by millions or billions of years. The practical challenge of detecting and confirming habitability, of moving beyond statistical estimates and theoretical modelling to empirical verification that specific worlds possess the characteristics necessary for life, depends on developing observational capabilities that can characterise planetary atmospheres, surface conditions, and potentially even biosignatures from distances measured in parsecs and light years, distances that reduce Earth-sized planets to points of light billions of times fainter than their parent stars, and that demand instruments operating at the limits of physical possibility. Atmospheric characterization, through transit spectroscopy, where starlight filtered through a planet's atmosphere during its passage across the stellar disk, carries absorption features indicating the presence of specific molecules, has already revealed atmospheric compositions for numerous hot Jupiters and Neptune-sized planets, detecting water vapor, methane, carbon dioxide, and even hints of clouds and hazes in these hostile worlds, and next-generation instruments including the James Webb Space Telescope and planned future observatories promise to extend these capabilities towards smaller, cooler, potentially habitable planets orbiting nearby stars. The detection of biosignatures, those chemical or physical features that indicate biological activity, presents extraordinary challenges given that many gases produced by life on Earth, including oxygen, methane, nitrous oxide, and dimethyl sulfide, also have abiotic production pathways through photochemistry, volcanic outgassing, or geological processes, requiring the identification not merely of individual molecules, but of chemical combinations in disequilibrium that cannot be easily explained through non-biological processes alone. Earth's atmosphere provides the template here, with its 21% oxygen concentration maintained far above the trace levels that purely geological and photochemical processes would produce, maintained instead through billions of years of photosynthetic activity that splits water molecules and releases oxygen while sequestering carbon in organic matter and carbonate rocks, creating an atmosphere in profound chemical disequilibrium that would collapse toward a low oxygen state within millions of years if biological activity ceased. Whether similar biosignatures would appear on other inhabited worlds depends on whether life elsewhere follows similar metabolic strategies, whether planets with life develop oxygen-producing photosynthesis, or rely instead on alternative energy sources and electron donors, and whether technological civilizations alter their planetary atmospheres through industrial activity in ways that create artificial signatures distinct from natural geological or biological processes. Synthesizing the multiple factors that determine habitability produces estimates varying across orders of magnitude depending on which assumptions about planetary formation, atmospheric retention, magnetic field generation, volatile delivery, stellar activity, biochemical requirements, and temporal habitability windows prove correct. A range of uncertainty that reflects the fundamental challenge of extrapolating from a single known example of life to a galactic population of hundreds of billions of stars and trillions of planets. Conservative estimates, applying strict criteria requiring Earth-like size, Earth-like orbit around a Sun-like star, plate tectonic activity, magnetic field protection, appropriate volatile content, and stable stellar conditions over billions of years, suggest perhaps several 100 million potentially habitable worlds scattered throughout the Milky Way, a number large in absolute terms but representing only a tiny fraction of the galaxy's total planetary population, and implying typical distances between habitable worlds of hundreds or thousands of light years. Optimistic estimates, accepting habitable zone rocky planets around red dwarfs despite stellar activity concerns, allowing for alternative biochemistries that might operate in different solvents or temperature ranges, including subsurface habitable environments in icy moons and water worlds, and recognizing that life might adapt to conditions considered marginal or hostile by Earth-based standards, expand the potentially habitable count into tens of billions or higher, suggesting that habitable worlds might be common enough that the nearest examples lie within tens of light years, potentially accessible to detailed observational characterization with future instruments, and conceivably within range of interstellar probes launched on voyages lasting centuries or millennia. The true number remains unknown, unknowable, without a comprehensive survey that current technology cannot yet achieve. But the question drives the development of new telescopes, new detection techniques, new theoretical frameworks for understanding planetary habitability, a new recognition that the answer, whatever it proves to be, will fundamentally reshape humanity's understanding of its place in the cosmos, either as members of a galaxy teeming with life in countless forms across countless worlds, or as rare inheritors of conditions so specific and so fortuitous that our existence represents an extraordinary improbability made manifest through the galaxy's vast scale and deep time, a single spark of complexity and consciousness arising in a cosmos mostly silent. Across these hundreds of billions of potentially habitable worlds, distributed through the spiral arms where star formation continues in molecular clouds and stellar nurseries, scattered through the ancient stellar populations of the galactic bulge where metal-poor stars formed billions of years before the Sun's birth, and even perhaps orbiting the isolated stars of the galactic halo ejected from their formation sites by gravitational interactions, the question of habitability connects to the deeper question of life's commonality, whether the emergence of self-replicating chemical systems represents an inevitable outcome, given sufficient time and appropriate conditions, a natural progression from prebiotic chemistry through increasingly complex molecular systems toward the threshold where metabolism, reproduction, and evolution begin, or whether life's origin requires extraordinarily improbable circumstances, a confluence of conditions so specific and so rare that the galaxy might host only a handful of living worlds, despite containing billions of locations where basic habitability criteria are satisfied. The current absence of evidence for extraterrestrial life, despite decades of searching through radio telescopes listening for artificial signals, through analysis of meteorites and returned samples from other worlds, and through increasingly sophisticated observations of planetary atmospheres and surface conditions, provides no definitive answer to this question. For the vast scale of space ensures that even a galaxy crowded with life-bearing worlds would present immense challenges to detection if that life remains microbial, if it never develops technology, or if technological civilizations prove short-lived or uninterested in interstellar communication. The Fermi paradox, the apparent contradiction between high estimates of habitable planet abundance and the absence of obvious evidence for extraterrestrial civilizations, has generated numerous proposed solutions ranging from the possibility that Earth's biosphere represents an early emergence of complex life in galactic history, to the suggestion that technological civilizations inevitably destroy themselves or retreat from active communication, to the recognition that the galaxy's scale makes interstellar travel and communication so challenging that even multiple civilizations might exist in mutual isolation, unable to detect each other across the light years separating their worlds. Each solution carries implications for habitability assessment, for if life emerges readily wherever conditions permit but rarely develops complexity or technology, then the number of inhabited worlds might be high, while the number of detectable civilizations remains low. But if life's emergence itself represents the rare step rather than the subsequent evolution of complexity, then even most potentially habitable worlds may remain lifeless, their oceans and atmospheres present but sterile, their geological cycles operating through billions of years without ever catalyzing the transition from chemistry to biology.